Okay, I'm gonna get started just to make sure I get through all the review. So the exam is on Wednesday this week. If you're not gonna be there, just let me know so we can figure out when you can take it earlier or whatever. I'll make sure I have it ready by tomorrow. There's no lab on Wednesday. Unless, you need to make something up, I guess you could do that. And you get one sheet of notes as a formula sheet. So let's go over the chapters that we need to review. So we'll start with chapter 22. So we talked about magnetism, so the magnetic field, the magnetic force on moving charges, the motion of charged particles in a magnetic field, the magnetic force exerted on a carrying wire, and loops of current and magnetic torque, and electric currents, magnetic fields, and Ampere's law, current loops and solenoids, and magnetism and matter. So all magnets have two poles, a north and a south. Magnetic fields can be visualized using magnetic field lines. These go away from north poles and towards south poles, and the Earth produces its own magnetic field. A magnetic field exerts a force on an electron charge only if it's moving. That force is charge times velocity times magnetic field times sine of the angle between them. And a right-hand rule, well, I think this is weird, but a right-hand rule, no, this is not that. Okay. Gives the direction of the magnetic force on a positive charge. So, the velocity, so velocity would be your index finger. Magnetic field be the direction you bend your fingers in, and your thumb would point in the direction of the force for a positive charge. Obviously, the opposite direction for a negative charge. So here's an example problem. What's the force on a charge of 15 microcoulombs moving at 250 meters per second at 30 degrees to a 0.3 Tesla magnetic field? So here, force is charge times velocity times magnetic field times the sine of the angle between them. That's between the velocity and the magnetic field. So 15 times 10 to the 6 minus 6 coulombs times 250 meters per second times 0.3 Tesla times the sine of 30 degrees comes out to 5.6 times 10 to the minus 4 newtons, or 0.0056. Now, charged particles in a magnetic field, if they're moving parallel to a magnetic field, they don't experience any magnetic force. If they're moving perpendicular to a magnetic field, they will move in a circle. And if it's moving in an angle, it will move in a circle around the magnetic field lines and continue along the direction. So it will move in a helix. And the radius of that circle is mass times velocity over charge times magnetic field. So if you have a 0.01 kilogram, 3 microcoulomb particle traveling at 4.5 meters per second, perpendicular to a 1.5 Tesla magnetic field, what is the radius of the circle it creates? So for this, radius is mass times velocity over charge times magnetic field. And the radius is the same for positive and negative charges. They just go around the circle the opposite direction. So 0.001 kilograms times 4.5 meters per second divided by 3 times 10 to the minus 6 coulombs times 1.5 Tesla. gives you 1,000 meters. So this would be a circle with a radius of 1 kilometer. In general, what we do is we make much lighter particles move much faster. Now, similar to the fact that there's a force on a charged particle, well, a current carrying wire has a whole bunch of charged particles in it, and you get a magnetic force that much like it follows a right-hand rule with current and magnetic field. So current times magnetic field times the length of the wire. Times the sine of the angle gives you the total force on the wire. So obviously a longer wire has more force, and then it's current times the length times magnetic field times the sine of the angle between them. So if you have 3 meters of wire containing 50 amps of current perpendicular to a 0.1 Tesla magnetic field, what would the force on the wire be? Again, force is current times length times magnetic field times the sine of the angle. So 50 amps times 3 meters times 0.1 Tesla times the sine of 90 degrees, because it's perpendicular. That comes out to 15 newtons. But yeah, you can get some dangerous stuff with wires with large currents running through them, because they also create magnetic fields, and so they'll interact with each other. So a current loop in a magnetic field can experience a torque, where you have a loop in a magnetic field, one side is pushed up, the other side is pushed down. And that torque ends up being the current through the loop times the area of the loop times the magnetic field it is in times the sine of the angle between the perpendicular to the loop and the magnetic field. So you get maximum torque when the loop is aligned with the magnetic field, and 0 torque when the loop is perpendicular to the magnetic field. And electric currents create magnetic fields, and the direction can be determined using a right-hand rule. Point your thumb in the direction of your current, the magnetic field curls around in the direction of your fingers. Ampere's law says that you take the integral along the path of the parallel component of the magnetic field. So you're adding up magnetic field times length. That will equal mu naught, which is a constant, 4 pi times 10 to the minus 7 Tesla meters per amp, times the enclosed current by the path. If you add up the magnetic field all the way around the path, the parallel component of the magnetic field, that will add up to the total current enclosed by the path. So if you set things up to be nice and symmetric, well, the magnetic field around a strong straight wire has to basically go in circles. By symmetry, it has to be the same, because if you rotate the wire, nothing changes. So your path can go around in a circle. And then you have the enclosed current. Mu naught times the enclosed current equals the length of the circle times the magnetic field. So the magnetic field ends up equaling mu naught times the current over 2 pi times the radius. And the force between current wires is between 2 current carrying wires. Well, you take force from one wire, and then you multiply by the current of the other wire times the length. So it's just mu naught I1 times I2 over 2 pi times the distance between them times the length of the wires. And that's why you can get some very dangerous situations if you have a lot of current running through two parallel wires, because this can get pretty big. So what's the magnetic field at 0.25 meters from a wire carrying 12 amps of current? Well, magnetic field is mu naught I over 2 pi times the radius. So mu naught is 4 pi times 10 to the minus 7 Tesla meters squared, millimeters per amp times 12 amps over 2 pi times 0.25 meters. That magnetic field ends up being 9.6 times 10 to the minus 6 Tesla. So here we have current loops and solenoids. The magnetic field of a loop looks a lot like the field of a bar magnet. And the field in the center of the loop ends up being N mu naught I over 2R, where R is the radius. N is the number of turns in the loop, mu naught times current over 2R. Now, a solenoid is a coil of wire that has essentially a constant magnetic field, uniform constant magnetic field inside and minimal magnetic field outside. And so the magnetic field inside of a solenoid ends up being mu naught times the number of turns over the length times the current, which is mu naught times the number of turns over the current. Mu naught times the, this N is the ratio of number of turns. This is number of turns per unit length times the current. So it's mu naught times number of turns over the length times the current. So what is the magnetic field inside of a 4 centimeter long solenoid that is with 800 turns when 3 amps of current is applied? So here, magnetic field is mu naught times number of turns over length times current. So that's 4 pi times 10 to the minus 7 Tesla meters per amp times 800 turns over 0.04 meters, because that's 4 centimeters, times 3 amps, which comes out to 0.075 Tesla. Now, matter can affect magnetism. So a paramagnetic material has no magnetic field, but will develop a small magnetic field in the direction of an applied field. A ferromagnetic field is like a paramagnetic material. A ferromagnetic material is like a paramagnetic material, only more so, where not only will it develop a magnetic field in the direction of an applied field, it can stick. You can have a permanent magnetic field. So when placed in an applied field, it can develop a permanent magnetization. And all materials have a small diamagnetic effect where they will generate a magnetic field opposite to the applied field. Any questions? Okay, I'll continue on with chapter 23. So this is about induced electromotive force. So this is where, a changing magnetic field can induce a current in a circuit. And the magnitude of that induced current depends on the rate of change of the magnetic field. So the faster you change the magnetic field, the bigger the current generated. And it opposes the change. The induced current will oppose the change. So to figure out how much change is going on, we need to understand magnetic flux. So magnetic flux, is how much magnetic field is passing through a surface. So that's magnetic field times the cosine of the angle with the magnetic field with the normal to the surface times the area of the surface. And the units are Webers or 1 Tesla meter squared. So how much magnetic flux passes through a square meter on each side perpendicular to a 3 Tesla magnetic field? So this is very straightforward. Flux is magnetic field times area times the cosine of the angle between the perpendicular of the field and the magnetic field. So that is 3 Tesla times 1 meter squared times the cosine of 0 degrees, which is 3 Tesla meters squared, or 3 Webers. So Faraday's law of induction describes how a changing magnetic field induces an electric current. The induced voltage or electromotive force is minus the number of turns times the change in flux over the change in time. It's negative because it will flow in the direction that opposes the change of the current. That's Lenz's law. So the more turns you have, the more voltage you'll induce or electric potential you'll induce, and the faster the change is. So change in flux over change in time. So final flux minus initial flux over final time minus initial time is sort of that. And Lenz's law says that an induced current will flow in the direction that opposes the change that created the current. So it will flow in a direction that would create a magnetic field. If the magnetic field is reducing, it would create a current that would make a magnetic field in the existing direction of the magnetic field. If it's increasing, it will be opposite the existing magnetic field. So a coil with 3 circular loops of wire, 0.1 meter in radius, is in a perpendicular 0.2 Tesla magnetic field. The magnetic field is decreased to 0 Tesla in 30 seconds. What EMF is induced in this coil? Well, we have 3 loops. We have an area, we have a circle that is 0.1 meters in radius. We have 0.2 Tesla magnetic field going to 0 Tesla in 30 seconds. So EMF is going to be minus number of turns times change in flux over time. So final flux minus initial flux over time times number of turns. So final magnetic field times the area times the cosine of the angle minus initial magnetic field times the area times the cosine of the angle over time. So minus 3. The final flux is 0 because it's 0 Tesla field. The area is pi times 0.1 meters squared. The initial flux is 0.2 Tesla times pi times 0.1 meters squared. The whole thing is divided by 30 seconds. And this gets an induced voltage of 0.0063 volts. Any questions about this? And this would be would create a current that would create a magnetic field pointing in the same direction as the starting magnetic field, because it would try and keep it existing. So a conductor that is moving through a magnetic field has an induced EMF that converts mechanical work into electrical work. And so that motional EMF ends up being magnetic field times velocity times length. Assuming it's perpendicular to the magnetic field. So if a bar is shot at 10 meters per second along a pair of rails through a 1 Tesla magnetic field that it is perpendicular to, how far apart are the rails if the induced potential between them is 5 volts? So here, the EMF is the magnetic field times the velocity times the length. So the length is going to be the EMF divided by the magnetic field times the velocity. So 5 volts divided by 1 Tesla times 10 meters per second gives a length of 0.5 meters. It's half a meter long. So generators and motors. Generators convert rotational energy to electrical energy. And the EMF produced by a generator is number of turns times magnetic field times the area of the loop of the, assuming this is for a simple generator, that's just a loop of wires spinning in a magnetic field. So number of turns times magnetic field times the area of the loop times omega times sine omega t, where omega is 2 pi times the frequency of the generator. And an electric motor is basically a generator operated in reverse. There are some subtleties, but they don't really matter for this class. There are other ways to do motors and generators, but this is sort of the basics. So here, if you have a 300 term, 0.25 square meter coil and a 0.5 Tesla magnetic field used as a generator, turning at 100 hertz, what is the maximum produced EMF? Well, the EMF of a generator is number of turns times magnetic field times the area of the loop times the angular velocity times the sine of the angular velocity times time. We want maximum produced EMF. That is going to be when the sine is 1. So that's number of turns times magnetic field times the area times the angular velocity. So here that's 300 turns times 0.5 Tesla times 0.25 meters squared. And omega is 2 pi times frequency, which is 100 hertz. So that's going to generate a maximum of 23,562 volts. And the root mean square of that would be 16,660 volts, something like that. Now, there's also a situation called inductance. Inductance is what's happening, this is specifically self-inductance. This is what happens when a coil with a change in current induces an EMF in itself. So a coil will resist a change in current by inducing an EMF to counter the change in magnetic field that occurs. So the definition of inductance is that the induced EMF is equal to the inductance times the change in current over the change in time. And so if you know how the EMF changes as a function of current, you can find the inductance for something like a solenoid. The EMF is minus L delta I over delta T. The inductance of a solenoid is mu naught, because it's going to oppose the change in current. Mu naught, number of turns per unit length squared, times the area, the cross-sectional area of the solenoid, times the length of the solenoid, or mu naught times the number of turns squared over length times area of the solenoid. So if you have a solenoid with 3,000 turns, that's 3 centimeters long, and has a cross section of 1 times 10 to the minus 4 square meters, what is its inductance? So that's 3,000 turns, a length of 3 centimeters, and a cross-sectional area of 1 times 10 to the minus 4. Well, the inductance is mu naught times the number of turns squared over the length times the cross-sectional area. So 4 pi times 10 to the minus 7 henries per meter times 3,000 turns over 0.03 meters times 1 times 10 to the minus 4 meters squared. With a bigger your inductive loop, the bigger your inductance. That is going to be 0.0337 henries, or 37.7 millihenries. An RL circuit is a circuit with a resistor and an inductor, which, much like an RC circuit, also has a characteristic time constant, where if there's a change in current, so if you change in current by you suddenly started applying a voltage, it will resist that change, so there'll be decay to that final resting state. So that time constant is the inductance divided by the resistance. And the current after closing a switch on an RL circuit is epsilon, the voltage over the resistance times 1 minus e to the minus t over tau. So that's voltage over resistance times 1 minus e to the minus t r over L. The energy stored in an inductor is 1/2 the inductance times the current squared, and the energy stored per unit volume of a magnetic field ends up being magnetic field squared over 2 mu naught. So how much energy is contained in a 15 millihenry inductor with 2 amps flowing through it? Well, the energy is 1/2 inductance times current squared. That's 1/2 times 15 times 10 to the minus 3 Henry times 2 amps squared. That is 0.03 joules. And then the other thing you can do with inductance is have a transformer. A transformer will allow you to use an alternating current and exchange voltage for current and current for voltage. So you can step up voltage or step down voltage. And the transformer equation is that, the number of turns on the primary side over the number of turns on the secondary side equals the voltage on the primary side over the voltage on the secondary side, or the current on the secondary side over the current on the primary side. So if a transformer has a primary coil with 1,200 turns and a secondary coil with 200 turns, if we put 1,800 volts on the primary side, what will the voltage of the secondary side be? Well, voltage primary over voltage secondary equals number of turns primary over number of turns secondary. So we're going to not worry about the currents, though you will get a much larger current on the secondary side. And voltage secondary will equal voltage primary times number of turns secondary over number of turns primary. And we get 1,800 volts times 200 over 1,200. And that's 300 volts. So by stepping down to fewer turns, we get a lower voltage, but more current. And chapter 24 is about AC circuits. So the voltage from an AC generator will vary sinusoidally. It will be some voltage maximum times the sine omega t. To represent that voltage, we could draw a phasor, which represents voltage or current in an AC circuit as it rotates. And its y component gives the instantaneous value of voltage or current. And the root mean square of a sinusoidally varying quantity is 1 over square root of 2 times the maximum value. The current of a resistor is voltage over resistance. So the current root mean square is voltage root mean square over resistance. And so if an AC generator has a maximum voltage of 200 volts, what is its root mean square voltage? Voltage root mean square is going to be 1 over square root of 2 times the maximum voltage. So 1 over square root of 2 times 200 volts is 141 volts. And the voltages that we express for like power in the wall and such are root mean square voltages. The root mean square current in a capacitor is voltage root mean square over capacitive reactance, which is 1 over omega times the capacitor. And the voltage across a capacitor will lag the current by 90 degrees. So the impedance in an RC circuit is the total impedance in an RC circuit, and the total, if you have an RC circuit, it will be current root mean squared will be voltage root mean squared over Z. The square root of R squared plus XC, capacitive reactance squared. So that's the square root of R squared plus 1 over omega C quantity squared. And the average power ends up being current root mean squared times voltage root mean squared times the cosine of the angle between them. So current root mean squared times voltage root mean squared times resistance over Z is what it turns out to be, because cosine phi is resistance over Z. So a 50 hertz generator with a voltage of a root mean square of 220 volts is connected to a 200 millifarad capacitor. What would the current be? Well, capacitive reactance is 1 over omega C. Omega is 2 pi times the frequency. And current root mean squared is voltage root mean squared over capacitive reactance. So that's voltage root mean squared over 1 over omega C. So voltage root mean squared times omega C. So 220 volts times 2 pi times 50 hertz times 0.2 farads gives 13,823 amps. This is a big capacitor. Now, for an inductor, it's sort of the opposite to a capacitor. The inductive reactance is omega L. And the impedance of an RL circuit is R squared plus XL squared. And inductance is 90 degrees ahead of current. So square root of R squared plus XL squared. And so that's square root of R squared minus omega L squared. And so the impedance of an RLC circuit with both an inductor and a capacitor ends up being XL minus XC squared. R squared plus XL minus XC squared. So R squared plus omega L minus 1 over omega C. And the resonant frequency, the point where this is going to have minimum Z, and so maximum output, maximum energy, maximum current for an applied voltage, that is where omega naught is 1 over square root of LC, because that is when omega L minus 1 over omega C equals 0. These cancel out. And that equals 2 pi times the frequency, of course. So what is the impedance of an RLC circuit with a resistance of 100 ohms, a impedance of 100 millihenries, a capacitance of 100 microfarads, and a frequency of 100 hertz. So Remember that Z is R squared plus XL minus XC quantity squared. So that's R squared plus omega L minus 1 over omega C squared. So that's 100 ohms squared times 2 pi times 100 hertz. That's omega times 0.1 henries minus 1 over 2 pi times 100 hertz times 100 times 10 to the minus 6 farads, which ends up being 100 ohms squared plus 62.8 ohms minus 15.9 ohms quantity squared. So 100 ohms plus 46.9 ohms squared, which comes out to 110 ohms. And the resonant frequency, what's the resonant frequency of an LC circuit with an L of 100 millihenries and C of 10 microfarads? Well, omega naught is going to be 2 pi times the resonant frequency F, which is 1 over the square root of LC. So 1 over 2 pi times the square root of LC. So 1 over 2 pi times 0.1 henries times 10 to the minus 6 farads is going to be 1 over 2 pi times 0.001 seconds, which comes out to 159 hertz. That is the review. I went through it a bit quickly. Are there any questions? If not, that is what I wanted to cover. The test is scheduled for Wednesday. If you can't make it on Wednesday at normal class time, let me know and we can schedule either you can come in on Tuesday or you can come in earlier on Wednesday and take it. I will get it ready by tomorrow morning. Yeah, either send me an email about it or just let me know right now. Okay, I assume you will send me an email if you need to take it at a different time. I will see you guys on Wednesday. Have a nice day.